And tonight we're joined by Andy and Ken Bone, and we're going to have a case study session in the second part of this webinar. So I'm just going to whiz through some of the technical bits because I realise some of this has been a little light, and you might want to just understand the technology before you go into your actual installations. So I'm just going to spend a little bit of time explaining the basic functionality of a heat pump and how you get heat out of it. We've talked a little bit about efficiencies and coefficients of performance, so we'll just touch on those again. We're going to compare the type of heat that you're getting out of a heat pump system compared with one of that's a boiler system, where you just burn fuel and get very high temperatures out. And because of that difference, what are the appropriate room heat emitters? Some of you might be interested in the choice of refrigerant, so we'll just compare those in terms of global warming potential. And then the one thing that I think everyone wanted a little bit more detail on was how to size it for domestic hot water. So we'll just quickly whiz through those because I know you're itching to get through to your case studies. So what is a heat pump? So I think we've explained that it's basically your fridge in reverse. So heat would naturally flow from a high temperature to a lower temperature, but if you put a little bit of work in, you can get that circuit working the way you want it to go. And in terms of the fridge, you can see that you have a cold zone and a zone that you're trying to keep cold and a zone that you're rejecting heat to. And the refrigerant circulates between the two zones, and in some cases it's a gas, in some cases it's a liquid. There are four main components to the circuit. You've got your compressor, which is basically a pump. You have a condenser coil. You have, which is this at the back, you have the expansion valve or a throttle device, and then you have your evaporator coil. And the electrical energy is mainly put into that compressor part. So hot refrigerant liquid passes through the expansion valve. Its pressure is reduced, and that causes it to go cold and start transforming from liquid to gas. Then the heat is taken out of the low temperature zone, as you can see, through the evaporator. The compressor drives the gas to a higher pressure, and you can generally, you know that phenomenon because you've pumped bicycle wheels before, and you can feel the pump getting warmer in your hands. So basically, when you compress a gas, you tend to raise the temperature of that gas. That heat is then rejected to the surrounding air at the back by virtue of condensing the refrigerant gas at the back of the fridge. And this is John Cantor's dynamic version of it. So here is your cold heat. So this is where your heat is absorbed, and this is where your heat is rejected. So in the heat pump, you're just reversing that that process. So the air source or the ground source is basically the environment that you're extracting the heat from, and that can be a cold environment, just like your fridge is a cold environment that you're extracting the heat from there. And that is outside of your property. it doesn't make the water as hot as your gas-fired boiler. A boiler is a very is a high temperature heat delivery system, but with a heat pump, obviously you can't get to those high temperatures. The fan, so in order to reject heat, in order to effectively condense outside, you also have a fan, and that's what gives you the noise outside. So that's just one consideration. And that's just another diagram. So let's just, so I think I've pretty much gone through it, but basically these are your three circuits. So you've got your water circuit to and from the house, with your colder water coming back from your radiators. It's picking up the heat from the condenser, and this is your and this is your fridge circuit here, and then your third circuit is basically your air circuit outside, or your ground loop, whichever you're using to extract heat from outside. So just again, a note about operating temperatures. Your boiler system will be delivering heat in the 60s and 70s, 70 degrees, and the difference in temperature between the average temperature in your system and the room that you're trying to keep at, say, 20 degrees, that's the delta T that we're talking about when we look at radiators. So it's more like a 50 degree delta T, whereas with your heat pumps, you'll be using sort of 35, 40 degree water. So that's just a 20 degree delta T with your room. So you can imagine for the same surface area and water flow through your radiator system, you're just not going to get the outputs that you're used to. And that's why we talked a little bit about retrofit in the last session, that to really get the most out of your heat pump system, you should be trying to reduce those demands of heating. Just a couple of diagrams so you can visualize this concept of coefficient of performance. We talked a little bit about this in terms of efficiency. So this, if you put a kilowatt hour of electricity in, and you get 4 kilowatt hours of heat out, then your COP at that point is 4. And another way of visualizing this is if you've got useful heat, which represents 100%, then what you're saying is you're putting in 25% of that through electrical energy. The rest is being extracted from your ambient, your outside or ground. The seasonal, so the COP is only meaningful for specific temperatures. So you have to define the source and the heat flow temperatures. So for example, it's 7 degrees outside and a flow temperature of 45 degrees C, and that's what your COP relates to. And if those two values aren't quoted when you're looking at data, then it's a bit meaningless. The other concept is the seasonal performance factor, and that's given over a heating season or over the year, and it's a measured annual efficiency of the heat pump at a particular location. these are references that come from a book by Dunbabin in 2013, if you want to look him up. And there is a theoretical best COP, and that's defined by the Carnot cycle. I think Tristan touched on this in his presentation, the Carnot cycle, but real heat pumps don't actually match the theory. COPs are at best about half the theoretical one, so that's what we've got to work with. And just a fun fact for you, we've talked about John Cantor and his website and his advice. Cantor happens to be Carnot rearranged, so there you go, who knew?
Look, Florence, can I just add that,
yes.
That there is a Carnot cycle equation, which is relatively complex, but if you simplify it,
yes,
it means that every time you double the temperature difference, you're halving the efficiency. So if, for instance, you're taking in, if the outside temperature is 10 degrees
yeah,
and you're putting stuff out at, your system's working at 35,
yeah,
that's a 25-degree difference.
yes.
If you take that to 50 degrees, i.e. it's 10 degrees outside, and you're trying to operate a heat pump at 60 degrees, would it be? Yeah, it would be. Well, then it's going to be a very inefficient heat pump because you've only got half the potential efficiency that you had when you're working at a lower temperature.
Yep.
Oh, and you've got all the figures here. Okay.
No, well, I've just got some examples of why that might vary, but that's exactly right. So if you have an air source heat pump in the winter to heat your bath water, your source temperature might be 5 degrees, your output might be 55 if that's what you're used to, although we'll talk about bath temperatures in a minute. Then your COP might only be about 1.5, you see. Similarly, so on the other hand, if you're using it in summer to heat a swimming pool, then your temperature difference is a lot less and your COP increases to 5. So that's the range of COPs that you'd probably be looking at for an air source heat pump. Ground source heat pumps are a lot more stable. The ground temperatures are a lot steady throughout the year, and that's why engineers like it. But it means you can get a COP of 4 if you've got underfloor heating or low temperature rads at 35 degrees, and if you're doing, at 45 degrees, you've got a COP of 3. So that just gives you a bit of a range of performance figures depending on the differences between those two, the cold and the warm zones. So this is just touching on the defrost cycle. So at low temperatures, the frost will build up on the evaporator bins, and a modern heat pump will automatically run a defrost cycle. So in that cycle, it's reversed so that it melts the ice on the evaporator, which is then the condenser, and then you go back to heating. And that's why Ken's talking about a buffer or having enough water in the system to take that inertia, really, to have that inertia and be able to still deliver heat to the house whilst that's happening. So it does contribute to a reduction in energy efficiency of about 10%, but it's obviously necessary because that frost will be problematic otherwise. I think that's all I want to say about defrost. Just a quick note on refrigerants. So refrigerants are sort of classified into hydrophilic fluorocarbons and other types. And there are regulations for those, and they should have no ozone depletion potential. These gases mustn't be deliberately released into the atmosphere. So ideally, you would never see any of this refrigerant leak, and leaks are quite rare, as I understand. But they have to be repaired quickly and by certified personnel. So just looking through some of these, so typically heat pumps are being sold with R410A or R143A, and some of the newer ones are switching to R32. So not only have they got zero ozone depletion potential, but they also have a lower global warming potential, and that's just defined in different ways. As we go to better fabric and lower heat demands, we can also look into much more friendly refrigerants, which are sort of ammonia and CO2. So hopefully that could be a consideration that you take into account when you choose your heat pump.
Can I just say, Florence?
Yes.
I certainly would be looking at models from manufacturers with the newer refrigerants now.
Yeah.
Some of the old ones. Not all the manufacturers have upgraded yet.
No, that's right. So have Mitsubishi and Daikin gone to R32? Or?
They have on some of their models. I've done my first R290 Valent last week,
right.
Which was quite a nice unit as well. Very expensive, but it is. I'm still running an old 410 system at home. Some of the older Mitsubishis would be a 410. It's fine, you know. It does what it's meant to. But yeah, the manufacturers are slowly changing over now.
Yeah, great. So I was just going to quickly go on to sizing. Did we want to go through any of the questions now, or shall I just carry on with the technical bits and we can go through questions?
I think if everyone's happy to wait for questions, that makes sense.
Yeah.
If you're happy with that, it gives you more space to have a good flow with your presentation.
No, oops. Great. So your sort of viability pointers are the same. I think we've been through this as well, but basically, have you got outdoor and indoor space available? Do you have noise criteria that you have to meet for planning? Your radiator sizes, have you included for some retrofit measures to make it more efficient? And we know that switching from oil is definitely economically viable, but do you understand that switching from gas may mean to start with that you're not necessarily saving on your bills, and there are ways to obviously counter that. But we're coming from the carbon co-op, and we think that from a carbon point of view, then that's definitely a justified move. Right, so Phoebe asked at the beginning of the session if I could just put up a diagram of how the system works, or how the system links up, really. So this is, I've just pulled this off the internet, so apologies if it's not completely right, but here we've got an outdoor unit with the internal unit here. So it could be that this is a split, or this is just in a hydronic section with a buffer. So you're doing most of your heat pump work out here, taking heat in, and then you are sending that heat either to your radiators or through to your hot water system, and then your water, you're drawing off your water when you need it. And you won't be able to do this, you won't be able to do a combi boiler, because that's just not feasible with these temperatures. So how do we size the system? Well, first you'd have to look at your heat losses. Now, if you were to do a whole house assessment with the Carbon Co-op, they would assess your current house, and that you might have seen a diagram like this. And what they will have done is taken the U values for your constructions, and you can do this for yourself perhaps. There's guidance on the MCS website, there's a design guide there, but Tristan also has some pointers and sources on his website if you wanted to go down that route. Or if you know your how your walls are built up, then you can download a U value calculator. It will take a little bit of time to get to grips with that. But if you just follow through with your material types, the thickness and the thermal conductivity of those materials, you build up your construction elements, and then you find the U value based on that whole build up. You can't add U values together. You can only add their inverse, so that the resistance to heat flow. Then you'll need, so don't forget your ventilation heat losses, and that's due to air coming in, cold air coming in from outside, and that could be just general infiltration leakiness, or because you've got fans running, so you need to take that into account.
Open chimneys.
What was that, sorry?
Open chimneys.
Oh, and open chimneys, yes.
That can double the heat load of a lounge or something sometimes.
Yes, of course, yeah. I think there are values for that, I think in the domestic heating guide, there's some ventilation rates for that, based on how many chimneys you've got. So on top of that, you'll need your areas for each heat loss element. Oh, and don't forget windows, of course. And the total heat loss is the sum of the U values times those areas, which is what's shown here, times the difference in temperature between outside and inside. And the design outside for Manchester, for example, is -4. So if you're trying to maintain 20 degrees whilst it's -4 outside, then your temperature difference is 24. So that would be the size of your heat loss would be 24 times, say, 553 in this case, which I think comes to 13 or 14 kilowatts. So then you've got to look at your radiator sizes, and for that you'd have to go room by room and do a similar exercise for each of those rooms. So in your whole house calculation, you can take into account internal heat gains and solar gains. Well, actually, probably not solar gains, just internal heat gains, because overall in your house, you will be able to manage that as a peak. But each radiator has to be able to do the peak for that room. So don't resist the temptation to size your radiators by taking into account internal heat gains. So when you've found your room by room, then you can check your radiator types and sizes. This is a chart that you can look up, and it gives you the typical output for when you have a boiler system. So that's at a temperature difference of 50 degrees between room and your average system temperature. From that, and you might want to take something off if you've added a few coats of paint to your radiators, then look up a radiator data sheet. If you know the models of your radiators, that's great, because you can just look it up. Otherwise, just find a typical one for that particular type of radiator, and find the equivalent output at a temperature difference of 20. It won't be proportional to the temperature difference because of the way heat is transferred at different temperatures. So yeah, so that's all I needed to say about that. Then we get on to domestic hot water. So John Cantor's website goes into this for a little bit more details, and there's some calculations and some simple experiments at home to determine your hot water demand and habits. But essentially there are two options. You've got your unvented domestic hot water cylinder, and that's generally sized on numbers of bathrooms or people. So with a heat pump, you would ideally use the correct type, and that would be optimized for those low temperatures going through. The Mixergy tank has an external plate heat exchanger, which is quite neat. Because we're not advocating really keeping your hot water at 60 degrees the whole time, which is what generally domestic hot water cylinders are designed to do, you would need some form of Legionella control, and that's generally just an uplift once a week for about an hour. And if your heat pump isn't big enough to do that uplift, then that would be covered by an immersion heater, or yeah, that's right, covered by an immersion heater. And the pressure that you get from your hot water cylinder is either just below mains pressure, because that's mains pressure that you're getting your water in at, or you can boost that with pump delivery. There's also so the second option is to have a thermal store, and whether you go for one or the other will be very different. It will be dependent on how you use things, but also how many sources of energy you've got. So for example, if you've got solar thermal or solar PV, or all of these things, you can just dump all the excess energy into your thermal store. It will need to be slightly higher temperature than the water you want out. So say you want to always deliver hot water at 45 degrees, you might need to keep it more towards 47, 48, just so you can get that heat transfer. And the hot water is literally pumped through pipes or a coil inside the thermal store, and is delivered a bit like it would be by a combi boiler, so mains pressure, and instantaneous hot water. But as you know from a combi boiler, it's not really that instantaneous, so there are things you can do to reduce the delay to the taps. And one of those things is to have small bore pipe work off a manifold. And that's the link to John Cantor's website there, with some more pros and cons that you can work through. So let's say you're going for a domestic hot water, solution, and this is a simple calculator that you can find online. And for this, you have to choose 3 variables: your water volume, the temperature difference coming between the incoming water, which we generally take to be 10 degrees over here, and your storage temperature, and then the time for heating all that volume of water up, so it's called your recovery time. So let's say you've completely emptied your tank of hot water because you've had a bath. It's the time for that cylinder to heat it all up again. Just make sure you use the right units. Being a mechanic, an engineer, I tend to work in watts and meters cubed and all that kind of stuff. But it might make more sense to use litres and degrees C. So there we go. But just make sure you've got the right units, otherwise it won't make any sense at all. Now, in terms of the installations themselves, I think we saw this last time. So you've got your ground source and your air source. You've got monoblock, so basically that entire refrig circuit is contained within the outdoor unit, or you've got your split, in which case your evaporator and your condenser parts are split between inside and out. So you then have to find a position for your outdoor unit, and then you might have a combination of these bits of equipment. So maybe the indoor unit or a buffer tank, expansion vessel, and then hot water cylinder or thermal store, and then integrate with renewables if you're going that way. And then in terms of controls and monitoring, you will get an app with each type. I can't tell you which are the best, but you can also integrate it with your own or add your own monitoring. So if you're going for the renewable heat incentive, you can go for additional grants that cover the monitoring and metering. So your installer will be able to advise on that. And you can use Tristan's OpenEM components if you're interested in more detail and just monitoring for your own purposes. So just before we get on, I don't know how I'm doing for time, Holly. Can't see the time.
Pretty good. It's just gone 6:34, or nearly gone 6:34. You're fine.
Okay, great. I was just going to go through a few examples, just so you can have some pictures in your head before we get onto the case studies themselves. This was the one in France that I showed you last time. So this is a low energy bungalow with underfloor heating. It's a 10-year-old split unit, and that's the hot water tank, which is integrated with the solar thermal panels there. That's the indoor unit and that's the outdoor unit. So if you can just picture that, this is that was an 8 kilowatt split, and this is an 8 kilowatt monoblock, and my friend who's just installed this is really pleased with it. She enjoys the comfort, but I think so, you know, that a lot of that is how it feels inside with the underfloor heating, and the fact that it's quiet. She did refurbish this bungalow, and she's a single occupier. So it's filled with cavity wall insulation. She's done the roof and the floor. The EPC says that she's got 8,600 kilowatt hours per year of heating demand, and the RHI pretty much covers the 7,500 installation cost. She's got a 150 litre domestic hot water cylinder, which costs her about 1,500. She switched to her electricity supplier for the agile tariff, and she's also got an electric vehicle, so that helps her with her charging. Her long-term plan is to have a power wall and solar panels, so it all stacks up from that point of view. The room thermostats are heat miser, which she said have driven her insane, but she's finally got the hang of them. These are all things that we will all learn to love and hate. And finally, she's also got an efficient wood burning stove, but I think that's more, yeah. I'm not sure what she's going to end up needing it, but it might just give a little bit more coziness. She does say the heat pump does make noise. You can hear it whirring away every so often, but only obviously when you're outside. So that's a recent and local installation there. And just so you can remember what a 16 kilowatt installation looks like, and this is monoblock, so you've got this, I want to say, monster outside. Just in case you were worried that that was the house behind it, no, it's just a barn. So it's not being it's not in the front of the house or aesthetically doing anything bad. But this was the buffer. This was the hydronic module, which also has the domestic hot water cylinder and the buffer tank, and that was with largely no insulation retrofit to the farmhouse. So that's the end of that part. So shall we look at some questions? Andy, have you managed to find some questions?
About your presentation, no, all very good actually.
Sorry, there are questions on the Q&A, so
sorry, let's have a look at the Q&A. I haven't opened it. I've been a bit right. A diagram to show how all the different parts for both heating and hot water,
yeah, we went, so
relate to each other. Yeah, I mean, it can be complicated, can't it, when you put it all together?
Yeah, I put up quite a simple one.
Well, yeah, one thing I would say is keep it as simple as you possibly can, because that way, more complex systems, sometimes you'll have built into them some sort of inefficiencies, and therefore you're going to get you can get a lower COP. I'm not saying it's always the case. For instance, one of the things that I'm quite into is using your heat pump to just heat your hot water up to a low temperature, and particularly if you've got PV panels, say your heat pump's running at 35 or 40 degrees, you heat the water up to that, and then you can heat again from that temperature up to your 50 degrees or whatever you want to use the water at. And then, of course, occasionally you're going to have to heat up to 60 degrees for Legionella.
Yeah. Okie dokie. So Anna's asked that she's looked on the website. It's recommended to find good ASHP for your house, but didn't address my main problem: shortage of space. What can be fit in a single tank? If I understand properly, it can contain coils to heat, warm the hot water, but can it also include the buffer tank to stop the thermostat returning on and off too often? So I'm not entirely sure. Can we get explaining what?
I'm here.
Oh, hi, Anne.
Hello. I'm sorry if it wasn't clear.
That's all right.
Yeah, I'm just very short of space, and I'm just wondering. I think you might have answered the question in a bit because you said you can have a thermal store, and that seemed to have the buffer tank kind of in it, and the hot water, the coils to heat the hot water. But I'm just can't get my head around it properly.
So is it internal space you're short of?
Internal
Outside,
space.
yeah.
I can manage. I think if I had one of those mono blocks you're talking about,
Yeah.
that seems to keep most of the stuff that can be outside.
Okay.
Lots of
And
space outside. It's
How much room have you got outside, Anne?
I've got a garden and things like this. So that's not really a problem. And I can have it in a place that's west facing. It's next to a small road, but there's no other houses.
Because sometimes you can actually build small outbuildings that are aesthetically in line with your existing garden, and put the hot water tank and maybe a buffer if a buffer is required in that building. Say, I don't know your situation, but if you had a combi boiler, so you don't have an airing cupboard, sort of that we would normally say would hold a hot water tank. We've actually just completed something like that literally 2 weeks ago, and so literally the same wall where the combi boiler was, on the outside of that wall we built a little sort of lean-to shed, effectively a very well insulated shed, but a shed, and we put the hot water tank in there.
What size would a shed like that be?
It's approximately about 600 deep by about 1.5 wide, and about, just a bit higher than an average door.
I don't think that would go where I'm thinking of putting it.
No, that's fine. I'm just making a possible suggestion, but
yeah, I don't. That wouldn't fit in the place I was thinking of putting it. And I've got. I'm going to have the whole of the house kind of reconfigured, and so I'll have a kind of meter square area going up to the ceiling that I've kind of allocated for the inside bits.
Are you a radiator system or underfloor, or will you become?
I was going to have underfloor heating downstairs. I've got storage heaters at the moment.
Oh, okay.
Yeah, because there's no gas.
If you've got them,
I was going to have underfloor heating putting in, and a couple of radiators upstairs. But the hope was that the heat from downstairs, because it's not a big place, the heat from downstairs, most of that would go upstairs. So the radiators upstairs would just be when it's really cold.
yeah.
Yes, no, you're correct.
Mm-hmm.
If you've got a meter square, I don't think you'll have a problem.
No,
You should be able to get a reasonable tank in there, which will, be. Because you could use just one combination tank, couldn't you, just to be a buffer and hot water?
Yes, but yes, that's what I'd want. But I'd also want, eventually, I'd like it kind of wired up, or whatever the expression is.
Oh, with
so that if I
immersion
get
heater in it.
PV panels,
Yeah, not a problem. You just get an immersion heater as part of the system. You just specify that.
Yes. No, I want an immersion heater. as well.
Absolutely, yeah. Go for definitely buy a tank that has, whether it's a thermal store or a combination buffer hot water tank. Make sure you've got an immersion heater in it, and generally they do come with them built in. So
okay. Now, what you've just said, is it going to be recorded? Because I haven't written that all down.
Everything's recorded, Anne, don't worry.
Okay, thanks. I
No
can
problem.
go back to that then. So it all sounds possible. Thank you.
And you've also asked how long does a typical defrost cycle last? I think it's just a few minutes, isn't it?
it depends. It does depend, and Andy will back me up on this. It depends on where it's getting the heat from to do that defrost cycle. So if you have just say, for example, your heating system decided to close all its circuits at the same time as that unit went into a defrost, it wouldn't be able to obtain any energy, or maybe not enough energy to do that defrost cycle. So that defrost cycle would potentially last a long time. And that's where the efficiencies tend to go wrong. But they're generally about 7 minutes, sometimes depending on how bad the weather is.
Yeah, that's what I had in mind. And then she also asks if a leak occurs, where is this likely to be? Aha.
A leak?
At a joint.
What, a refrigeration leak?
Yeah.
Chances are it might be a component that's failed. If it's a split system, yeah, there might be a weakness on the connections that the refrigeration engineer may have made. But generally, it is very rare, as you said in your presentation. It is very rare that you would lose refrigeration. You can't see it. If it's a tiny leak, the unit will just deteriorate in performance. It may not give you an error straight away. I think I've mentioned this before. It may not give you an error straight away until it really loses a lot of refrigerant. And by then you might notice that your hot water is not hot enough, or it's doing some really odd things. And then eventually an error should come up on the controller saying there's a problem.
Cool, thank you. Do different refrigerants affect COP much?
Yes.
They will, yes. Just by virtue of being a different
They have
different physics, don't they?
yes.
Different refrigerants have what I call a window of workability. So some work better at high ends, some work better when the ambient is colder, and with the onset of the new refrigerants, they tend to have a much larger window of performance, as well as they have much larger temperature window as well. So you can actually run some refrigerants up to nearly 65 degrees now.
Yeah, cool. Don asks, is it possible to use heating degree days for a locality to help size the actual heat pump required? So the way heating degree days work is for consumption over the year. So it's more about the area under the curve rather than the actual size of the unit. So the kilowatts that we're talking about here in terms of how big your unit is, that's the power that you put in. It's a rate. So it's, that's the graph, the line on the graph. Whereas the consumption is whatever you're using over time. So it's the area under the graph. So one of the things I was going to say is, if you've got, for example, your kilowatt hours over the year, you can't work back from that to a heat pump size, because what you don't know is how peaky your profile is over that year. Whereas if you've got the profile of how you're using something, then obviously you can work out your consumption.
Yeah, I think this is an issue to do with the what your coldest days are like, rather than what's happening over the whole year, as Florence was saying. And there is this thing about if it's going to be very cold, you want to have some arrangement for that. the way I look at heat pumps is that I don't actually, because some people go down to 24, 25 degrees. So if it's -5, you want to be at 20 degrees, you need to something which will cope with that 25-degree differences. But I only do 20 degrees on the grounds that it's very rare that you're going to have a day where it's freezing all day. And so if it is freezing all day, you've got, and your heat pump is very, if you like, finely attuned. Most of them are oversized anyway, but if it is finely attuned, then your temperature could drop below 20 degrees to 18 or whatever. And you have two options. One is to have a fan heat. Well, I've got a wood stove. An efficient wood stove is great, but if you haven't got that, you could have a fan heater and plug that in for the 1 or 2 days a year that this happens. Or two, you could get a duvet and snuggle under the duvet when it's down to 17 degrees or something. But actually, as you've seen from my other presentations and so on, that you're better not trying to get a system that will allow for every eventuality, because then you'll be oversized and the whole thing will work inefficiently. I was recommended an 11 kilowatt heat pump for my house. I installed a 5 kilowatt and I've never had a problem with it. I've never been a day that I've felt, oh dear, the heat pump's not working, and in fact, I've never run it continuously for more than, say, 7 or 8 hours. And I only run it for 7 or 8 hours when I come in and it's cold because I've come from something, and then I need to heat the house up to a reasonable temperature. Yeah, it's my answer to that one. Somebody mentioned pipe sizes. We can talk about pipe sizes if we want, can we? Or...
We've got quite a lot of questions. Do you want to institute an order so we don't miss them out? Or do you want to go on to pipe sizes?
I think, Polly, if you organise that.
Yeah,
you do that. Yeah.
Pipe sizes was a misunderstanding, because I was talking about microbore pipes, but only in relation to domestic hot water, not radiators.
It wasn't a radiator fitting.
Supply of hot water, isn't it? Yeah.
Nor was it underfloor heating related, was it?
No.
Okay, just to clarify. Great. There's quite a few still. So I don't know if you want to grab the most recent ones and work our way backwards, or what makes most sense, what's easier for people to do. I find that easier, so I'm afraid the person who should be next is going to be last, just because it's much easier to see. So Don's asked, it might help to avoid oversizing a heat pump and improve the efficiency. Is it possible to get daily day information from Don?
We've just done that, haven't we?
Have you done that one? Okay. Do you generally? Sorry, I can't hear very well on this headset. Do you generally have to pay for a heat pump survey from Carla?
From who?
It is going that way.
It is going that way, yeah, because there's so many requests. Is that right? Yeah. Because
to do a proper heat loss and RHI projected payment takes a lot of time. So some companies are now charging for that effect. You could then take that and use that. You have now this policy, and if you sign up with that particular company, they tend to waive the fee, or you can take that report and take it to somebody else.
That's a great question. So it's sort of an incentive, for people to stay with one company. Yeah.
But also, I mean, a heat loss survey is essential. Otherwise, you don't know what size of heat pump you need.
Absolutely.
So you've got to do that, somehow. I mean, you can't, because don't Carbon Co-op do that or something? I mean, that's...
Yeah, they do. Yeah, that's part of what they provide as a part of the kind of holistic sort of energy survey. Yeah.
Can I ask, what price would you expect to pay for this? I think, well, Ken might know, but I think one customer was asked to pay £250. Is that about right?
Yeah, I was going to say about £200. We currently don't do this at the moment. We do a very quick whole house sizing and maybe an indicative quote it then becomes a bit more serious, we then will do a complete full survey for the property, with maybe a site visit as well. Depends how complicated the project is potentially going to be.
So Christopher's asking, so what size pipes do we need for radiators? Well, that really does depend on your heat demand. But
and number of radiators, and also the other thing is how many circuits you've got.
Yeah.
The more circuits you've got, the better, because if you've got 2 or 3 couple of radiators on a circuit, well then you know the first one's going to be hot, the one's going to be slightly less hot. But if you've got 10 radiators on one circuit, well, by the time you get past the 4th or 5th radiator, you know all the others are going to be fairly cool. So having 4 or 5 circuits or more, depending on the size of the house, obviously, it is a good idea. And then it might be you can get away with 15mm pipes, on each circuit, so that you've got several circuits, and so you don't need to go for the larger size pipes that you'd need if you were only doing 1 or 2 circuits.
Cool.
If your existing system, say it's a gas boiler system, is working well and you have no problems with radiators that are struggling, then normally chances are it should be okay for a changeover. If the client is already saying that the extension we put on 10 years ago, the radiators have never quite worked correctly, then chances are it's exactly what John's just said. It might have been added to the end of an already existing long radiator run, and they're just not getting sufficient flow and heat to those radiators and the extension. So that would then be a problem already for the gas boiler, and that would also manifest across to a heat pump installation as well. So we would have to address that in some way.
Right.
So next we've got Asaru, who's asking, how do you use the same thermal store for both hot water and space heating? Right, yes, trying to get my my diagrams in my head. So from the hydronic part of the heat pump circuit, you can have you can put hot water directly into your thermal store, and that's just it's a bit like a buffer tank, so you can use that to sort of draw heating water off there, or hot water, domestic hot water. So your circuits don't mix. Your hot water circuit doesn't mix with your heating circuit, but it's being basically heated by the hot water in the thermal store, which is also being used for your radiators. Does that make sense to?
Yeah.
Yeah. Ken, have you seen that?
Yeah, thermal stores are not really a big player in the heat pump world at the moment. I think now with the new refrigerants and the higher temperatures that the heat pumps can produce, thermal stores are now coming back into play, or being seen as maybe a potential component. The problem we find with with thermal stores is obviously if you have a big heating load, you could quite quickly deplete that, and then your hot water may struggle. And also your heat pump is already working quite hard to maintain that thermal store at a decent temperature to give you the same hot water, as well as trying not to let it go too low, so you're not losing heat through your heating system and your hot water at the same time, if that sort of makes sense. So in my experience, though, the heat pump tends to have to work a bit harder than it would normally do if it had a separate cylinder and then a separate heating circuit.
Can we have a quick check? It's 7 o'clock now. We've got 3 case studies, and I don't know how many questions we've got, but I'm just, how long are we going to go on to? And then,
well, I thought we could move on to the case studies now. There are a couple of questions which
fine.
we could.
There's just 2 more questions in the main Q&A, and then we capture them all in the chat as well, so we can send feedback in writing, so we can keep to time.
Very quick comments on the 2 more questions, or?
Yeah, let's just. So Julian says, while they're obviously a lot pricier than a water tank, could a heat battery work for Anne? I think Anne was struggling with space, but I think we've discovered that she actually did have space for a water tank, so that wouldn't be necessarily an issue. I'm not sure.
You could potentially have a metre square cupboard that's full floor to ceiling, so that sounds pretty good to me.
Move to the next one.
Yeah, and then how do sun amps for hot water storage affect efficiency versus using a hot water tank? What temperature do you have to heat to get the heat into the sun amp?
A lot hotter to change the phase changing material at the moment. They are working on a lower temp design, but it's very similar to the thermal store situation where the heat pump would have to be constantly running pretty much at its max to change that material in the heat and in the sun amp, because it goes from one state to another. There isn't really an in between, as much as I know. I haven't played around with them enough to give you any true experience on it, but I do know they have to be, the heat pump or the heat source feeding the sun amp has to be run at quite a high temperature.
Okay, shall we move on?
Yeah, someone asked, can there be a run for air conditioning, as in reverse? You can have a reversible heat pump, but you will have to have different emitters.
Yes, they can. My experience is it can get messy because you're generally dealing with chilling of a wet system, and you could put as I think you were going, Florence, you could put in a diverter valve that could send it to some wet fan coils or something like that. But it's a lot more thinking about insulation. You can't just put standard insulation in because those pipes will sweat, is what we call it. And they only run down to about 14, 15 degree flow temperature. So they're not actually like an AC unit. They're only like a chilled device.
I mean, that's a lot easier with air to air, isn't it? I mean,
it is.
It's completely straightforward then.
Yeah.
But then air to air have their limitations. Great if you've got an open plan ground floor and you want to just warm the whole floor up with warm air coming in. But yes, that's another topic.
It can be done, but it's not. I wouldn't call it air conditioning. I would just pass it.
Okay.
We call it comfort cooling.
Yes. Why not? Yeah.
Right. So we have got 3 case studies. Thank you to Margaret and Alex and Alan for providing those. And so we've been given some detail, probably, but not enough, obviously, to give a full diagnosis. But we're just going to go through the various things that we would look for when we start our different approaches to a similar problem. And so I'm just going to put up a few details about each case study and then open it up to Ken and Andy, and we'll just discuss it as a panel discussion. So Margaret has a 186 square metre house in Cambridge. Oh, and the nice thing about these three are we've got Cambridge, York and Manchester, so we've covered the country, which is great. I managed to pull this off Google Maps, Margaret, I hope you don't mind. She's provided some drawings, which I'll show you in a minute. Now the orientation and form factor aren't particularly favourable in terms of you know, huge amounts of beneficial solar gain, but also lots of heat loss area. So in terms of a retrofit, that's quite a tricky geometry. So there's nothing she can do about that. So we'll look at the insulation works that she's done. And then there's a mixture of radiators and underfloor heating, and she's got some top-up sources of heat, so log burners, and happy to have electric heaters. She has got a quote from an installer who thinks it's about 70 watts per square metre, and he did take a slightly conservative view of the treated area, so came up with a much larger unit. And then we've got some possible plant locations. So the air source heat pump outdoor unit could be in the front garden, which I assume is here where the shrubs are. The gas boiler is currently in a corner of the house in the utility room, and then there's a hot water cylinder in the loft, and there's quite a lot of storage space up in the loft eaves, and there are 3 kilowatt peak solar panels facing southeast, I believe. These are the drawings. So we've got quite a lot of rooms, and as you can see, lots of heat loss areas here and here, but there is external insulation. This is where the boiler is, right in the corner over here, whereas I think the hot water cylinder is over here in the loft, so quite a way away. Right. Would anyone like to, so can we let Margaret speak a little bit?
Okay, well, I've got a question actually about the 70 watts per square metre.
Yes.
I mean, to me, that's where I would start, is to say that sounds as though somebody's plucked it out of the air. It needs a proper heat loss survey, as we've discussed earlier.
Yes, or Margaret, if you fancied taking it on, you could try and work out your heat loss from your house, because I think you know your build-ups, don't you?
Yes, I have looked at it and wondered for Cambridge what you would use for the lowest temperature. I think it's -1, or would it be below colder?
You mean design temperature? Oh, yes.
Yeah, design temperature. Yeah.
Well, again, I'd design for 0. I mean, Cambridge isn't especially cold, but then if it goes down below, you know, it might go down to -5 or whatever.
Yeah.
I mean, where I am up in the Pennines, it does occasionally go down to -10 and whatever. But, you know, those are exceptional days, and I have exceptional circumstances. If you've got a log burner somewhere, well, then you're going to be able to cope with that type of thing by huddling around the stove.
And a couple of electric radiators if necessary. That would be acceptable.
Yeah. And there is evidence from BRE that your heat pump will work more efficiently if you use, you know, electric radiators than if you oversize it to account for going down to -5 or further.
So I think there's a lot of negotiating to be done here about, you know, just how how much heat loss there is and how big a heat pump we want.
That's right, because I would think you could get down to a 10 kilowatt heat pump or less, depending on what
Yeah.
that actual figure is. If you go for 10 kilowatt, there is a very nice system that Mitsubishi make, where it's actually 2 5 kilowatt heat pumps working in tandem, so that most of the year only one of them's working, and then when you get the cold weather, they both, if you like, sort of come in to cope with that heat loss.
But is the outdoor unit double size? Because we're a little tight. I could get a sort of standard, 1200 wide, but if it's a great big double unit, I'd have trouble with that.
I mean, it's not much bigger than, it'll be bigger than an 8 kilowatt unit, which is only one fan. But when you go up to the 11 kilowatt, for Mitsubishi anyway, that is 2 fans anyway. So there's not much difference in size between that and the 10 kilowatt one.
Yeah.
But the 8 kilowatt one, if you can manage with it, might be a better option.
That's what I was wondering, if we could really go down to 8 and push it. We've got underfloor heating. We don't want it to be too hot, to the temperature to be too hot. And we also have a diverter from the solar panels. And that tends to work quite well, and to keep the tank warm for several days. If there's a sunny day and then some overcast days.
Is that a hot water tank you're talking about?
Yeah.
Yeah, so I mean, that's great.
Solar integrated one.
We've just got a twin coil and a diverter. Yeah, so it's an immersion heater with immersion heater that comes on with the solar diverter. So that works very well.
Okay.
And if you're running, I don't know what type of underfloor heating you've got, but some of it will only run up to 40 degrees. So you set your heat pump at 40, not to go above.
That's what I understood. 35.
Yeah. And then what you can do off that circuit, you can have water heated up to 40, and then when it goes to your solar the solar diversion system, it's already heated up to a reasonable temperature, and that will be really good in the winter. In the summer, you might want to change it back or something. I don't know, but
how do you get to prevent the water from overheating? Part of the underfloor has got ceramic tiles. I'm not so worried about that, but we do have some engineered oak, and I don't really want that to be affected by that.
Keep it below 40. Have that on the circuit from the heat pump, which won't go above.
And how do we get enough hot water? I'm not sure.
Oh no, the hot water's on a separate circuit. You want to keep that separate, don't you? Hot water through the hot water pipe.
Okay.
And do have a play of the hot water cylinder calculator that you can get your 210 liters up to temperature within a reasonable time limit. I think social housing, you can go up to 4 hours recovery time, so you can play with the recovery time just depending on your own habits, basically.
Yes, well, 210 is enough for us. I don't know why we would be wanting a bigger tank. He seems to be suggesting another 100, which I don't see the point of. They're separate circuits, so why it has no effect on the heat pump, does it?
It may be because it's a solar cylinder, and obviously a heat pump generally works at lower temperatures. So you need to use more of the hot water stored to get your comfort temperature in when you're washing. You're not blending so much cold with it. So they tend to put more capacity in to accommodate that. But saying that, your solar thermal, it is solar thermal you have.
No, it's not. It's just PVs with a diverter. Just a diverter to the
Oh, you've just got a PV, like
to the immersion heater, and diverter to the immersion heater.
Something like that. Okay, so yeah, I mean, it's entirely up to you. As you say, if we take into account people's lifestyles as well as, you know, we have to follow some rules and regulations, but we do listen to people's lifestyle, and they say, you know, we don't want the house too hot, or we want the house tropical, and we don't use a lot of hot water, or we do use a lot of hot water, and we try and make a judgment and guidance on based on figures.
Another question was, we've had the boiler way in the back in the utility room. It used to be in the kitchen, and then we've put the tank right up in the loft, so they're miles apart. Does that matter? Should we be looking to organize that?
It does.
To reorganize.
I'm looking at the drawings and being a bit concerned about, because even if you put the heat pump in near the front of your garden, that is a long way to get all the way up to the tank. I mean, Dakin only runs about 10 or 12 meters between the indoor between the outdoor and the cylinder.
Only 12, because I've understood about 30.
Yeah. It all depends.
I thought I would come across the front garden, go up within the EWI, external wall insulation, and then just go straight in the loft floor to the tank, to the the hot water.
It's not recommended.
But it's tall. It's way up there.
So I was thinking of maybe.
Sorry, what's not recommended?
To have a long run between the heat pump and the cylinder.
Yeah. Okay.
I was thinking more. Maybe an option would be a split system, and you could replace the existing gas boiler with a hydro box, and then you run refrigerant between that and the outdoor unit, and some of those run up to 50 meters between the two. Yes.
So a hydro box inside.
Yes.
If I could put that in the loft. I could get that in the loft and keep it all in front.
You could put that in the loft near the hot water cylinder and run the fridge pipe, as you say, under the cladding. And
there's room there. I mean, I wouldn't like to lose it, but I could.
Yeah.
Okay, that's interesting. Thank you. And then I would just, I've got to make the pipes work in a different way than if the source. Well, no, it's all coming from the tank anyway, so I'm all right. Yeah.
So
okay, that's great.
That's great. Don says, Margaret's problem is surely a good case for using available degree day information to assist in sizing heat requirements. I think I understand what you're saying now, Don. So Margaret, you could look at degree days and how many days your the temperature outside is
nasty.
Is below below 0 or 1, and see how you can you can cope with that, basically.
Well, because we're the house is kept warm, we're not out at work. It tends to stay quite warm once we get it warm, and so we can tide over if they're quite cold days. But I mean, we're going to have less heat with the heat pump.
Heating, you'll have inertia in the system. So
yeah. And the EWI is quite effective upstairs.
Oh, I was wondering what the EWI material was.
It's just expanded polystyrene.
Okay, so
nothing very exciting. Sorry.
No, but it'll be high performing for that thickness.
Yeah, it is. It is.
That's right. Good.
Yeah.
Cool.
Okay.
Fantastic. Thanks, Margaret.
Thank you.
All right.
Right, and then we've got Alex in York. Is he on the line? I can't. Oh, yes, he is. Yeah. So Alex has got a 120 square meter end of terrace in York. It's a 1968 building. The gable end is unfilled cavity. Front and back sides are insulated but not very thick. Timber frame walls with hanging tiles. There's a well insulated extension, 100mm PIR in cavities that covers 2/3 of the gable end wall. Good double glazing everywhere and triple glazing in the extension. extra insulation envisaged internally at the weakest point. So that's envisaged in the near future. But the your main concern, Alex, I think, was with the. So you've got a quote, or you've been told you need a 11.2 kilowatt heat pump in order to heat the hot water quickly. So it's worth looking into. I think your hot water requirements. You've got 2 bathrooms, 4 occupants. You say 2 of which like to shower for a bit longer, and are they teenagers by any chance?
Yes, they are. Yeah.
Did you say anything about getting? I think I've got here about PV possible in the future.
Yeah,
because I would, just sizing your heat pump according to your domestic hot water, it will run pretty inefficiently.
I agree.
Yeah.
And so thinking about using a diverter from the PV panels to heat up the hot water, I think would actually be a better way of doing it, right?
Yeah.
And the other thing though is that again, as in the last case, you need a proper survey for the heat loss, so you know what your heat loss is. And I should imagine actually with what you're saying here about the insulation you've got and you're putting in, that you probably get your heat loss down to somewhere where you could use a 5 kilowatt heat pump.
Right.
Partly I'm taking it because your house is the same as mine in size. Mine's up in the Pennines and it's an old stone house and it's not amazingly well insulated. And I do very comfortably on a 5 kilowatt heat pump. So I would suggest that obviously you want a solution for the domestic hot water, and that's, yeah, if you sort that out, I think you'll find what are you gonna, yeah, I mean, if you've got 25 watts per square meter, what does that end up at? I know, yeah, you should be okay, I think, on that one.
Well, I was going to get on to.
Oh, we're going straight to Alan's, are we? Fine.
Because you can't see the image. Sure, the image. Oh, no.
Oh.
This is Alan's.
Oh, there we are. Okay.
This is semi,
Yeah.
and it's 140. So, Alex, I'm not glossing over yours. I'm just going to say, in terms of hot water demand, you might be similar, but in terms of heat loss, Alan's has. Oh gosh, why did it do that? I think I'll just go back to this view.
Right.
His current house is 90 watts per square meter, according to his home energy plan, which Carbon Co-op have done for him, and so that would be a peak of 13.8 kilowatts. But with some of the agreed improvements that we're doing, so it's a mixture of internal and external insulation, floor insulation, MVHR, some new windows and doors, draft proofing and loft insulation, we're managing to reduce that peak load down to 28 watts per square meter, which is 4.3 kilowatts.
Brilliant.
Yeah.
Can I just make a comment for Alex on this? That your house is slightly larger than Alex's, and what you're ending up with is a 4.3 kilowatt heat loss. It might well be that Alex is going to end up with something similar to what you have got in terms of heat loss.
Yeah.
So that would help in terms of sizing his house.
Yeah, just
sizing his heat loss.
Just take just make sure you don't underestimate sort of infiltration and ventilation, those kinds of things. If you're not planning on putting any mechanical vent with heat recovery, that can be quite a big discomfort. But yeah, I agree, Andy. I think there's no reason why you can't get down to those levels. And then, so Alan's question was very much about the domestic hot water as well. We've run a few calcs because that's what I do. I've just looked at sort of, you know, if you had a low flow shower of 6 litres per minute, and that is an energy efficient shower, and you had to heat up the water for 4 of those 5-minute showers, we're talking about 120 litres. You could also say it's a 35 litre shower, and that gives you an upper band of 140. A warm bath is 180 litres to the middle of the outlet, the overflow. So if you consider that you're displacing water and maybe your temperature is a bit less, because you don't want it any more than 38, 39, then that's about 134 litres. So really, if you had a 150 litre tank, you would be covering those demands.
Right, all of that. Yeah.
So using that little calculator or doing it this way, whichever, then you can see that you're getting.
Can you explain the energy input? I couldn't understand that figure.
So that's just your mass times your specific heat capacity times your delta T.
Is that kilowatts or kilowatt hours?
That should be kilowatt hours. You're right. Yeah.
Right. Okay.
Yeah, I've put that in as an image. So it was kilowatt hours. I don't know why I changed it. So that's the energy input that you put in. And to work out the peak rate of input of energy into that, then you divide it by.
Well, if it would be 5 hours if it was a 5 kilowatt.
That's
heat
right.
pump, wouldn't
yes,
it?
Sorry.
Yeah.
Yeah. But that's not the recovery time.
Recovery time. Yeah, 1.7 hours is from.
So when I used, I have to. When I used the calculator, the recovery time calculator, it came up with these figures, and I ended up dividing by 3.6, but I can't remember why.
Okay.
It's getting late, and I can't.
It's snowball effects, isn't it? You're starting from cold, but as the temperature warms up in the tank, your delta T is closing.
Yes.
So it actually accelerates as it gets near the end of its process.
Okay, that's what it is.
Right.
So actually, if you had a 1.5 hour recovery time, then the size of your air source heat pump is 4.7, and you might, if you were being traditional like I tend to be, you might add a bit for efficiency losses, or you could really insulate your tank, or get a really insulated tank and not worry too much about that in the meantime.
There's 4 of us in our house, and we run a 250 tank on an air source, and we've never run out of hot water.
You have a 250 tank on a 5 kilowatt air source. Yeah. So there you go.
Takes about 90. I mean, to be honest, I've never actually depleted it right down to 10 degrees and then timed it back up to full temp. But it just does its thing. Going back to Alex's query about he's been told that he needs a bigger heat pump. That's for hot water recovery. That's generally gas boiler torque.
Right.
We would do that.
That's a big problem, isn't it? That people have still got this gas boiler mindset. And sort of,
I would suggest he perhaps changes, if he hasn't already changed his tariff, and then he could maybe load the hot water tank to a high temperature during the night.
Yeah, I did suggest that to the installer, and I also said worried about cycling and that being inefficient, but he just kept banging on about the hot water and that people complain about not having enough hot water. And
but that is boiler thinking, I'm afraid. Your biggest energy consumption is your heating. So
yeah,
that's what we need to focus the efficiencies on is your heating. Yeah, for me, the hot water bit is almost a secondary irrelevance. Yeah, we need hot water. You know, we have one shower a day, 50 litres, it's 200 litres. You know, that's, you know, I'm not worried about how long it takes. I mean, I suppose it would be if it took me 4 hours to heat a tank, but we never have consecutive showers in my own family enough to warrant it being a problem.
Yeah. Oh, that's good to hear.
Does Alan want to come in at all and ask any questions? I don't know if he's unable to chat. Possibly not.
Should be able to.
Yes.
Muted.
Yeah.
Am I unmuted? Right.
Yeah, go for it.
Right. Sorry. Yeah. Yeah. Thanks for all of that. Yeah, I was just really wondering if you could have a discussion about the hot water cylinder versus thermal store. Again, I think a few people have sort of wondered how that works temperature-wise, but it sounds like you're advocating having an immersion to top the temperature up, or have separate systems. So yeah, if you could maybe discuss that, that would be useful.
Yeah.
Is the thermal store that's been suggested to you, Alan, is that because they think you need some volume for your heating circuit?
That was my suggestion. So no, we were just Alan's just had a report with the options, and we haven't made a decision, but the two options open to him, as are open to anyone, were the domestic hot water cylinder or the thermal store. So we're just looking at what would apply most to him at the moment. But I mean, it looks like a domestic hot water cylinder would cover your needs, Alan, in terms of your showering. I don't know. We haven't actually had a conversation about.
Is it because you think you're going to be lean on hot water, or you don't have enough space to get the height in of a conventional cylinder, or is it?
No, it's just purely what's going to work best, really. I mean, in terms of efficiency and so on. I suppose in the back of my mind is half the year you're looking at hot water only, and if you've got a thermal store, are you then heating a lot of heat capacity for no reason?
That's a fair point, Alan. So the thermal store would work well in tandem with a solar PV installation, because what it means is you can, but actually, to be fair, you can just dump your any excess solar energy you can put into the domestic hot water cylinder now with PV diverters and stuff. So yeah, I mean the two options are still available, but it sounds to me like the hot water cylinder would work just as fine for your case.
I mean, I'm not against them at all. It's just my logical thinking is, obviously the hot water part is at the top where the hot water coil or plate is, and the cooler part is at the bottom, which is where you want to take your low temperature heating circuit from potentially, but the heat pump is still having to potentially meet that high target temperature to maintain that load at the top.
Yeah.
So I need to actually get a hold of one day and run into a system and play with it. I'm afraid I'm still stuck in conventional cylinder with immersion, and then that immersion we can link into PV, or even if it was Octopus. I know Octopus Agile hasn't quite had some negative nights recently, but we did in the COVID period, and I was switching everything on during the night, and loading things up as much as possible. So you could do that with both a hot water tank and a thermal store. So, I can't comment and give you any data on it, experience data on that.
But again, there's an argument for using the electricity from the solar to heat the water from whatever temperature it comes out of the heat pump, say 40 degrees, to whatever you want to use it at, because you've only got a low lift. And anyway, if you were pushing the heat pump to that, you wouldn't get a brilliant COP out of it. And with the heat pumps, every time they change over from doing one thing to another, you're getting losses anyway. So sometimes it can be easiest just to run it at one temperature, and then particularly when you've got PVs, use that power to raise the temperature there. Obviously in the winter, you're not getting so much off the PVs, but most of the year you'll be getting something.
Yeah.
Great. Okay, thanks.
No worries. So the other, well, we touched on it, but the other plus for a thermal store is not having to do the Legionella control, because obviously you're not using that water directly, and you're getting instantaneous hot water out of your taps. So that's the only other thing. So there might be a calculation to do to see what the trade-off is in terms of energy, but it sounds to me like a lot of people are making hot water cylinders work more efficiently. So we can discuss it as part of the next stage. Great. Well, it's 8:20, and I think we've pretty much covered everything. So I just wanted to say thank you to Andy and Ken for stepping in, and to Polly for organising it all, and all to you for turning up yet again and sticking with us. So have a great September.
And
thanks everyone.
Thanks to all, Flo and Ken, and to Polly too, because well organised, it's worked well.
Yeah.
We've learned a lot. Thank you for joining, everyone. We'll send you the recording from today, and we will definitely capture all your questions from the chat and revisit those. And I think, Florence, is it fair mentioning you're running another heat pump session, aren't you, on the 30th? Is that right?
I believe so.
Yeah.
It will be a whistle-stop tour, and sort of condensing pretty much everything we've done.
So it's not over yet. And there is also the green grant session that's happening tomorrow night for anybody who is sort of considering that, and obviously in combination or alongside RHI, which we've touched on a lot. So it could be something worth signing up to. So feel free to check out Carbon Corp's Eventbrite events, and we can obviously link you to that. We'd be more than happy to welcome you. We love solar thermal. Good comment. It is an excellent source of clean, renewable energy, even though people think we don't get enough sunshine.
No, but you can cover about 50% of your use using solar thermal, so it is.
Yeah.
I have a very clever architect friend who heats his entire house through solar thermal.
Oh wow!
Really? That's phenomenal.
Good. Yeah.
Can be done.
It's on a vertical facing, south facing. It's got about 7 panels, seven banks of panels through a 500, 600 litre thermal store, 3 low temperature blended circuits off of that. So it's very close to passive. I wouldn't say it is a passive house, but it's close to passive.
Right. Well done.
So, Ken, is solar thermal better in the winter? You know, like in the winter,
Yes.
with PVs, you get nothing much at all, but you're getting relatively getting a bit more out of solar thermal. Are you?
We recommend if you have a small roof, you get more. You're going to get more energy long term out of a solar thermal system than you would a PV.
Right.
And I'm looking at carbon zero homes and finding the same. So you know, if you cover most of your 50% of your hot water through solar thermal, then you're making the most of your most of your roof as possible, and the rest with PV. So there we go. Cool.
Brilliant. Thank you.
Fantastic.
Brilliant.
Right. Okay. Thanks for that, everybody. Folks.
Thank you.
Right.
We'll be sending out a feedback form for anybody who's still on the call, just to forewarn you. So that will be really useful just in terms of any kind of continued conversations and sort of as a bridging device in a way for Florence, maybe leading into anyone coming to the session on the 30th as well. And we'll try and capture some more answers from any of the questions that might be still open in the chat. So I've copied all of those, and we will be sort of capturing them on paper and sharing any responses as well in the sort of as an attachment in the minutes along with the recording from tonight. So it's been really, really useful to have you all involved. And for anybody who wants a referral as well, obviously there are energy assessments continuing with Carbon Co-op in Greater Manchester. So feel free to send any requests through. And there is a little bit of feedback around those needs on the form that I'll send through to you as well, on the feedback form. So just to forewarn you, but it's not a big form, I promise. But yeah, many, many thanks to Andy for calling this into being, and Florence and Ken and everybody who's contributed and joined and put time and effort and energy into this. It's been really, really interesting. Hopefully we can do something very similar again soon, or have a recap in the future, because it's, yeah, I think it's a really positive way to support people to try new things and to try and understand the complex world of heat pumps. It is quite complex. Quite a journey.
They're very simple, actually. It's complex in getting them fitted to existing housing stock.
Yeah, it's the nuance, isn't it, in the case by case of actually doing the work of getting them fitted in your home rather than the actual system. That's the interesting thing. Okay, well, I'll let everybody have a good rest of your evening, and we best call it a day just because it's 2:45. But yeah, many thanks, and we'll be in touch tomorrow. Anyone got any last comments? Sorry, Ken.
No, that's fine. I just said thank you very much. Please do be in contact. I'm happy to assist in any way I can. So.
Right. And bye from Andy.
That's really kind. Yeah, thank you.
Thank you.
Goodbye, everyone.
Bye.
Good night, everybody. Thank you.
Bye.